So let us discuss about graph coloring. Okay. So initially, let us start with a map here. So you have a map in which you can see 5 regions. Now the question is how many number of colors you need to assign to these regions so that no two adjacent regions have the same color. So the answer is 3. Okay. So how do you proceed? For example, the middle one, assume that you fill with blue color. Okay. Now the regions which are adjoined to the region C are B, A, D, E. Okay, so I cannot take this color to any one of these A, B, D, E, right? So let me pick up another color for B. So let me color this with red. Okay, and this I'd like to color it with red. Now I'll go the coloring of A with green. Okay, so now we colored this map with 3 different colors so that no two adjacent regions are having the same color. Alright, now we can convert this question in terms of graphs, in terms of coloring vertices of a graph. Now, so let us see how to convert this map into a graph. So now what you have to do is you take these regions as vertices. Let's say the region A, B, C, and similarly D. If two regions are adjoined, then they will be connected by an edge. So here we will have so let me take C, A, B, E, and D. I'm taking 5 vertices. There are 5 regions, right? So now C is adjoined to all, right? So let me establish connections here. So how about A? A is adjoined to B and D. And D is adjoined to E and A. And when it comes to E, it is adjoined to B. So what we have here is the graph K4. So the graph here is K4. Alright, now to color, now how many ways can you, how many colors do you need it to color the vertices so that no two adjacent vertices receive the same color? So initially I can observe one thing here. You can observe that the vertices C, D, E, they are mutually adjoined. I mean, C and D are incident with an edge, and similarly C and E is incident with an edge, and D and E is also incident with an edge. So I cannot assign 2 different colors just to these C, D, E. Definitely we require 3 different colors for these. Okay, if C assigns some color, the last picture, okay, so I assign C blue color, right, and D red. So red color to D and green color to E. So whenever you find mutual adjoint vertices, then you can easily see the minimum number of colors required to color this graph. Okay, so minimum are 3. Now let me see, are these 3 colors enough? Yes. So what we can do is, I can't assign red color here. So to B we can assign red color, whereas for E we can assign green color. Okay, that's it. So we have assigned colors to vertices. Okay, so whatever graph that we have drawn here using these maps, we call that is a dual graph of this map. Okay, so the graph corresponding to the map is called dual graph. So now let us look at one more map. Yeah, this one. So how about this map? And what is the dual graph of this map? So how many vertices are there? So let's draw the vertices. So these are the vertices. Let us assign edges correspondingly. So this is the dual graph of this map. All right. So now, like in the previous case, can you find any mutually adjoint vertices? I mean, adjacent vertices. I hope you can look at A, B, C, D. Yeah. So you can look at A, B, and C, and D. All right. Now, how many colors are needed to minimum number of colors needed for K4, so that no two adjoint vertices have the same color? So we need 4, because you take any vertex here that is incident with every other vertex in this graph. Okay, so therefore minimum are 4. All right, so you better to identify such block first. So the minimum colors required are 4. That's it. Now, can we proceed with these 4 colors? So here I am assigning red color to A, and let's assume yellow color to B, and green color to C, and blue color to D. Okay. Now how about G? I hope we can assign red color to G. And E cannot be assigned red color and also blue color. So it can be assigned either green or yellow. Okay, suppose if I give green color here to F, all right, now this one can be given yellow color. Okay, so when it comes to the vertices, so let me assign the colors. So to A I assigned the red color, and for B, for C assigned green, and D blue, and B yellow. Okay, so now you color the other vertices also. So the other vertices, so G we are coloring with red, and then F we can color it with green, and this you can color it with yellow. Alright, there is other possibility also. We can even assign, we can assign red color here, and we can assign yellow color here, and a green color here. That is also possible. Okay, now this completes our job. All right, now coloring maps totally converts into coloring vertices of the graph. Okay, so now we're going to define a graph coloring. A graph coloring, we mean coloring of simple graph is the assignment of colors to each vertices of the graph so that no two adjacent vertices are assigned the same color. That is what we mean by graph coloring. Okay, so we have already seen some examples, right? Now we define a chromatic number. So the minimum number of colors required for graph coloring. So the least number of colors needed for coloring of a graph. So we are going to denote that with chi of G. So chromatic number is denoted with chi of G. So for example, now I'd like to see what is chi of K2. What is chi of K2? Chromatic number of K2? Yeah, 2. K2, it means you know, right? There are only 2 vertices and you have an edge between them. Now you can simply assign 2 different colors to it. That's it. Okay. So the chromatic number of K2 is 2. How about the chromatic number of K3? 3. Good. Chromatic number of K3 is 3. And of course, you can easily tell me the chromatic number of K4. So in a complete graph, every vertex is adjacent to other vertices. Therefore, as many number of vertices you have, that many number of colors we require. Okay, so chromatic number of K4 is 4, and similarly the chromatic number of Kn, that is going to be n. All right. Now let's assume that a graph is bipartite. Let G be a bipartite graph. Okay. So now what is the chromatic number of G? If G is bipartite graph. So that is 2. We define bipartite, I mean, we have seen an if and only if condition for bipartite graph, right? If you can assign one of the 2 different colors to each vertex so that no 2 adjacent vertices are having the same color, then we call that, I mean, then we can say that G is bipartite. G is bipartite, then it has to satisfy this condition, alright? And if it satisfies this condition, then G is bipartite. Right? So the chromatic number is bipartite graph is 2. Even if you look at the chromatic number of Kmn, that is complete bipartite graph. What is chromatic number of Kmn? That is 2. That's it. Because you forgot about whether it is complete or not. First of all, bipartite graph. Okay. All bipartite graphs have chromatic number 2, whether they are complete or not. Okay. So now, if you take a planar graph, right, how many number of colors we require to color the graph? Okay, so that question is answered by this 4 color theorem. Chromatic number of a planar graph is no greater than 4. So if the graph is planar graph, maximum we need 4 colors, that's it. You take any planar graph that can be colored with maximum 4 colors. Not maximum, sorry, minimum 4 colors. Maximum you can use as many number of colors as you have vertices. Okay, so I must say minimum. So maybe we can look at one problem, one planar graph. So let me take a planar graph here. Is this a planar graph? Some are saying yes and some are saying no. And those who are saying no, think again. You can simply do one thing, no? You just take this vertex here. Okay, then this line goes here and this line goes here. That's it. So this is a planar graph. Okay, and there is a trouble if I keep a line like this and if I keep a line like this. Now is it planar? Now there are some thumb ups I can see. So what is it you need to do to make it planar? I mean, to show that this is planar. A, B, C, D, E, F. Okay. So what are the adjustments you are going to make? So where the intersection is happening, just you see this, simply we can take this BD edge, you take just BD edge, okay, and you connect it this way. That's it, this became a planar graph. Now no need of changing vertices also, just you adjust that edge. Okay. I think you got confused with the isomorphic isomorphic one. I hope you must have remembered this problem. These two graphs are not isomorphic. That's what we proved. This graph and the earlier graph, what we have seen, these are not isomorphic. All right. Now let me color this graph. So first tell me how many colors I required. Minimum number of colors required here. I hope it seems like 2 colors are enough. Is it? Is this graph a bipartite graph? Okay, let us start assigning colors. I'm not finding any three vertices which are mutually adjacent to each other, right? So let me assign red here, then I will go with blue, and this I must go with blue. Then okay, you go with red here, and this must be assigned red color, and this can be assigned blue color, right? So the graph is bipartite graph here. 2 colors are enough. Therefore, chromatic number of this graph, the chromatic number of this graph is 2. All right. So whatever planar graph you take, you do not require not more than 4 colors. Okay. So remember one thing, this 4 color theorem is applicable only for planar graphs. You can't apply it for some random graphs. Okay. For example, if you take Kn, as many number of vertices you have, that many colors we need here. Okay. But of course, one thing we can say, if there are n vertices, you do not require not more than n colors. Whatever graph it may be. Alright, but our aim is to use the minimum number of colors. Alright, now I'd like to ask you a question. So how about Cn? What is chromatic number of Cn? I hope you know what Cn is. A cycle with n vertices. So is it 2 always? Are you sure? Okay, if you say 2, what is chromatic number of C3? tell me the chromatic number of C3. For C3 it is 3. Then how can you say it is 2 for sure? Yes. Now it depends on whether n is even or odd. Okay. For example, if you take C3, definitely you require 3 colors. Alright. Whereas if you take C4, now I hope 2 colors are enough for C4. What you can do is you can assign red color here. So the red here and the red here, and we can assign green. That's it. So 2 colors are enough for C4. And when it comes to C5, so what will you do? You start with 1 color here. Now you know how the edges are there. Okay, then you will go with color. Let me go with green color here. Okay, then this I'll go with red color, and this I'll go with green. But here I cannot assign red color again, and even I cannot take green color again. Okay, so I should invite one more color here. You understand why? Because there are odd number of vertices here. Since there are odd number of vertices, and you cannot assign just 2 colors in this cycle, so minimum 3 colors are required. Whereas if it is even, 2 colors are enough. Okay, if you start with red color, finally you can end with the green color, and that green is adjoined to red. Fine. Okay, so the chromatic number of a cycle, so that is 3 if n is odd, and it is going to be 2 if n is even. Okay, so now I'd like to ask about wheel. What is the chromatic number of wheel? I hope you know what a wheel is. You take a cycle, and in the middle you take one more vertex, and you connect the new vertex to all other vertices. So that is a wheel, WN. So how many colors do you require? 3? Or 3 enough for a wheel? Alright, now let's do one thing. Let's look at a wheel here. So this is W3, right? So the W3, so now you can see the W3. Alright, so definitely what do you do here? You need to assign you need to assign 3 different colors here. Okay, to the outer vertices. Even the new vertex is adjacent to every other vertex in the graph. So I cannot go with any one of the colors which are assigned here. So I must think of a new color for the new vertex. Okay, so therefore it is very clear that chromatic number of W3 is 4. So how about chromatic number of W4? Yeah, so this is W4, right? Okay, you're saying 3. Now first you can find the mutually adjacent vertices. So you assign 3 different colors, because I hope you can find 3. Yeah. So now these 3 colors can work for the other one, right? So here I cannot assign red color here, but blue color also, but I can assign green color. So this vertex can be assigned green color, and this vertex can be assigned red color. Yes. So therefore the conclusion is that chromatic number of W4 is 3. So how about the chromatic number of W5? See, it is as simple as this. You know the chromatic number of Cn. So what you know is it is 3 if n is odd, and it is 2 if n is even. Now what is happening? You are in Wn, you are taking one more vertex and you are connecting that vertex to every other vertices, right? So in Cn, if you use 3 number of colors, in Wn you must use 4 colors. Yeah, exactly. The chromatic number, you can say Cn plus 4. Yeah, so that is what the chromatic number of Cn plus 1. Okay, so that's what it is equal to 4 if n is odd and 3 n is even. Okay, now let us walk with an example. You can see the question, what are the chromatic numbers of the graph G and H which are shown below? Here you can see graph G as a subgraph of H. So first you complete with G and later you can go for H. So the answer for G it is 3 and for H it is 4. Alright, now let me try to do it. So you can see that this ABC, okay, so you can see a triangle here. ABC are mutually adjacent to each other. Therefore, what we can say, 3 different colors are required. Minimum number is 3. Okay, so I'm taking 3 colors. Like I don't know whether you can see or not. Red is 1, blue and green. So next, what shall we do? So the next thing, you see the vertices which are not adjoined to A. So the, I can see E, F, G and D also. Alright. Suppose if I assign red color here, let's assume if I assign red color here, does it work? To E I am assigning red color. Alright. So in that case, I cannot use one of the green or blue colors here, because the green is here and blue is here, so definitely, so I must assign red color to D. Okay, so you cannot take red color either here or here. Okay, so next you cannot take blue here, so yeah, you can take blue here but not green. So let's assign green and then blue here and definitely red here. Okay, so this procedure you need to write in terms of words. Alright, therefore, the chromatic number of this graph is 3. So how about the chromatic number for the graph H? So what is H here? Just this A and G got connected, isn't it? To the chromatic number of H. So in case of H, we got the new vertex. From here to here, right? So since A is given red color, now G is not allowed to give red color. So now what shall we do? So and also I cannot assign green or blue here because this G is adjacent to E and F also. Alright. So now we need a new color for this vertex G. Right. So now we are going to assign new color here. All right. So the minimum number of colors to graph to color H are 4. Okay. Therefore, chromatic number of H is 4 and the chromatic number of G is 3. Now let us see an application of this graph coloring. Okay. So for scheduling of examination, we can use this graph coloring. So that is in the case when you have courses in which the common students are there. Okay. Now how those exams needs to be scheduled. For example, if you have a course list in which you do not have common students, then no issue. For one day you can conduct the exam. Okay. See, for example, you have 1, 2, 3. There are 3 courses. All right. So here the course 1 and course 3 have common students. Okay. Now I don't want to combine. Shall I combine? Yeah. So the course 1 and course 2 also have common students. Now how should I conduct the exam? How many minimum number of days I require to conduct the exam? So now let us convert this problem in terms of graphs. So the course 1, course 2 and course 3. So I'm taking the courses as edges. So if there is a common student in the two courses, then we will have an edge. If there is no common student, then there will be no edge. Okay, so 1 and 2 have common students. Even 1 and 3 are also having common students. Okay, now how are you going to plan the exams? How many days do we require here? So in the day one, so let us conduct course 1 exam. All right. So in the day 2, so let's conduct the exam for courses 2, 3. But if I conduct it like this, so let me illustrate by taking the persons so that the things will be clear. So this is course 1. Let's assume that A, B, C, D, E. These are the students we have. All right. So for the first course, the students who are registered for the first course are, I'm taking randomly. So let me take more number of students. So that I'll have more convenience. Okay. So A, B, C, and E. These are registered for the first course. All right. And when it comes to the second course, the people registered for the second course are A, C, D, G, H. So they have common students. Now the common students here are the courses 1 and 2, A. That's it. I hope A is only common. There I have taken B, C, E, right? Okay. So the common student is A here. If you want, you can take one more student. So now let me take the students in the course 3. Okay, this is C. Yeah, C is also there. A, C. And how about course 3? So now remember one thing, there are no students which are common in these two courses, 2 and 3. Okay, no student is common in these two courses. So we can conduct the exam at once for courses 2 and 3. So now, so I cannot take the people who are in 2 or in 3. Okay, so except A, C, D, G, H, you can take the others. Who are the others? B, C you are not allowed to take. E we can take. F, that's it. Okay, so now 2, 3 courses do not have common students, therefore exam can be conducted at once. Do you understand? So you can see that no student is common here and here. All right. So now the day one you conduct the first course. In that case, A, B, C, E will write the exam. Okay, others will take rest. And while conducting the exam 2, 3, okay, we are not having any common students. There is no issue here. All right. So now, if you want to face this kind of situation, like having number of courses and the common students in it. Now, if you are planning to schedule the exam, we would like to know how many minimum number of days we need it. So simply take the courses as vertices, and if two courses have common students, you connect them by an edge, and you color the graphs. Okay, so the vertices with the same color, it means the vertices with the same color, those are nothing but courses, right? The vertices are nothing but courses, right? So those courses can be conducted exam at once. Red color vertices can be conducted exam at once. Other color vertices can be conducted exam at once. All right. Now let me give you one more situation. Now in this case, now I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm taking more courses. All right. So now the information given is 1, 2, 3, 8, and 4, 9. Yeah. So these are what. Now you tell me how many minimum number of days you require to conduct the exams for these 9 courses. So you draw graph. 4, 6 we have, 1, 6 we have, 2, 7. Yeah, 2, 7 also we have, 1, 5, 3, 8. 3, 8 and 4, 9. Okay. So 9. So 9 here, we can establish 4, 9. So next 3, 8 is left. So this is 3. Let me take 8 here. Alright, so 3, 8. So now how do you assign colors? So initially you take one vertex, 1. You assign the color red. And I hope 7 can be assigned red color. Okay. Not only 7, 4 can be assigned red color. 4 or 9, anything. And 3 can be assigned red color. Okay, now let me take another color. So this is assigned blue, 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 and this is also blue, blue. Now just 2 slots are enough. So we require only 2 days to conduct the exams. So what are the exams you are going to conduct on first day? On day 1, you go with the courses 1, 7, 4, 3. On day 2, we conduct the courses 2, 5, 6, 9. Okay. Even though you have 9 courses, just 2 slots are enough for this situation. Because course 1, 7, 4, 3, they do not have any common students. The students who are writing the course 1 exam are not registered for course 7 and also not registered for course 4 and not registered for course 3. So those who are writing the first course, they are not registered for 3, 4, 7 courses, so no issue. And even similarly, those who are writing the course 7 exam, they are not registered for 1, 4, 3. Therefore, no issue. All right. So just 2 slots are enough to conduct these examinations. Now let us look at an algorithm which help us to color these graphs. Okay, so that algorithm is known as Welsh-Powell's algorithm. So in which what you have to do is, so initially you need to write the vertex list and the degree list in a non-increasing order. Okay, you take the graph, you find degree of each vertex and arrange the degree in a non-increasing order like this. List of vertices and the degrees down to it in a non-increasing order. So now you take the vertex which has most degree. 1 minute,